You remember matrices? Let's take some matrix 1, 2, 2, 1. Okay? A matrix is something that takes in vectors, produces vectors, and this is a matrix that will take in what kind of vectors, produce what kind of vectors?
2 cross 1, 2 cross 1.
2 entry vectors and produce 2 entry vectors. Let's operate this matrix on the vector, let us say 1, 1. What comes out? I shouldn't forget my notation. Operation requires brackets. What comes out? 3, 3. So if 1, 1 goes in, what comes out is 3, 3, right? In this matrix, if 1, 1 goes in, what comes out is 3, 3. This is interesting because 3, 3 is a scale of 1, 1. Yes? We don't know what interest that is of, but at least we note that something interesting has happened. 3, 3 is a scale of 1, 1. Okay? Let's try something else. 1, 2, 2, 1, same matrix. Let's say what goes in is 1 minus 1, the vector. Calculate what comes out. Very fast. What came out? Minus 1, 1. Do you agree? Minus 1, 1. So if 1, 1 went into that same linear function represented by that matrix, 1 minus 1 went into the same linear function represented by the matrix, what came out is minus 1, 1. Again you see that phenomenon occur because minus 1, 1 is a scale of 1 minus 1. How much of a scale of 1 minus 1 is it? It is the minus 1th scale of 1 minus 1, correct? 1 minus 1 scaled by the scalar real number minus 1 produces this vector, correct? Now you might start wondering, oh, maybe this is always going to happen. Maybe this is always going to happen. 1, 2, 2, 1. Let's try something else. Let's try 1, 2, for example. What comes out? Hmm? 5, 4. Is 5, 4 a scale of 1, 2? No, it isn't. Okay. So just because this surprising thing happened for 2 vectors doesn't mean it's going to happen for all vectors. Okay. These 2 vectors seem to have some kind of special interesting property associated with them. Some special interesting thing happening with them that caused them to come out as scales of themselves. Now, do you think 1, 1 will come out as a scale of itself for all linear operations? No. You can easily think of a matrix where 1, 1 will give something that doesn't have the same entries. Correct? Correct. So this 1, 1 coming out to be a scale of itself is also something that specially occurred for this matrix, correct? A vector that comes out a scale of itself for a given matrix or a given linear operator is called an eigenvector of that linear operator. Okay? So this 1, 1 and this 1 minus 1 are eigenvectors of the matrix 1, 2, 2, 1. Okay? Both of these are eigenvectors of that matrix. Is it okay? This is a definition. It's a new definition. You are not supposed to have known it unless you had it in the previous class. But I gave you the definition. Write down the definition. A vector that when operated upon by a matrix comes out to be a scale of the original vector is called an eigenvector of that matrix. Is the definition okay? The definition is okay? No problems? Now what is the scale? What is the scale corresponding to this eigenvector, for example? It came out 3 times itself, correct? Yes? So the scale here is 3 times. What is the scale here? Minus 1. So the scale here is minus 1, correct? Yes? This scale is called the eigenvalue corresponding to the eigenvector corresponding to the linear function. Okay? It's just a definition. Maybe if you remember your linear algebra lecture series or something, maybe you remember it as this, Ax equals lambda x or something like that. Anyone? Yeah? Something like this, right? So this A is our matrix 1, 2, 2, 1, x is that 1, 1 and lambda is 3, correct? So Ax equal to lambda x is what we are talking about. Nice. Can you think of other eigenvectors of the same matrix? 3, 3 is an eigenvector, you think? He thinks 3, 3 is an eigenvector. Who agrees that 3, 3 is an eigenvector? Okay. And how did you come up with that?
Because it says 3 times 1, 1. So if you operate it on 3, will come outside. You'll get 3, 3.
Yeah, by what reason? Yeah, by the scale invariance or scale homogeneity of the linear operator, right? If you have some eigenvector, then any scale of that eigenvector is also going to be an eigenvector. Correct? So specifically, for example, 3, 3 will come out how much? 9, 9. You see that? 2, 2 will come out? 6, 6. Correct? What will be the corresponding eigenvalue? Eigenvalue will be 3. Okay? So if something is an eigenvector, then all its scales are also an eigenvector with the same eigenvalue. Okay? Worth writing this. Write this down. If some vector is an eigenvector, all its scales are also an eigenvector with the same eigenvalue. By the way, one thing to note is that for us to even ask the question, is there an eigenvector, what is the corresponding eigenvalue and so forth, the number of inputs and number of outputs of a matrix must be the same. Otherwise, you cannot have a vector coming out the scale of itself, it doesn't have the same number of entries, correct? Yes, which means that just in mechanistic terms, it has to be a square matrix. Correct? Which means number of rows and number of columns have to be the same. That's just another way of saying number of inputs and number of outputs must be the same, or number of entries in the input vector and number of entries in the output vector must be the same. So look at this specific situation. One eigenvector is this fellow 1 1, correct? 1 1 the vector. Okay. What happens to this input? This input becomes 3 times itself. Correct? Another eigenvector is 1 minus 1. This fellow. What happens to this fellow? It goes in the other direction, flips by the same amount, correct? Now, if I ask you what happens to something else, let's say this vector here. This vector here, it's not an eigenvector, so it will not come out in the same direction. But could you somehow analyze this vector in terms of the eigenvectors? You can see that happening, right? So, you could represent this vector as a combination of this vector and this vector, right? And what happens to this component? It stretches to 3 times. And what happens to this component? It flips. And so quickly, at least intuitively, or in a geometric intuitive sense, you can quickly figure out, oh, what is going to happen to this vector here? This will become 3 times and this will flip around. So my vector will be there somewhere. Okay, so, and that gives you at least a quick geometric intuition of what is going to happen. Otherwise, you don't have any geometric intuition of what is happening in that space. Okay, so in some sense, eigenvectors build geometric intuition. Okay.
Can you not build the intuition with any other vector also?
Yeah, there are many other ways of building geometric intuition, that is true. And so I'm not saying eigenvectors are the only way of building geometric intuition. There are other methods, there's something called a singular value decomposition, very different kind of geometric intuition. There's various ways of building geometric intuition about linear operators. We are currently focusing on this concept of eigenvectors. We are going to ask ourselves, do convolutions have eigenvectors? Okay. Convolutions are linear operators, correct? They are linear shift invariant functions. You remember that? So they are linear. Are they linear in the sense of taking in an input and producing an output of the same vector type or the same space? Yes, because they're taking in a signal and produce a signal. Yes? And so the question is at least well formed. Does a convolution have an eigenvector? Okay? It's infinite dimensional, so calling it a square matrix would be strange. But still, I mean, a signal goes in and a signal comes out. And so the question of whether the output signal is a scale of the input signal is a valid question to ask. Okay? So we are going to ask ourselves, do convolutions have eigenvectors? Let's start with a simple convolution first. You have an input signal going in, you have some output signal that is going to come out, and I give you the convolution, just one non-zero line with a weight of 1, or multiplier of 1. Okay? Does this convolution have an eigenvector? What is the eigenvector? Any signal is an eigenvector. Why? Because what does this convolution do? Just produce the input at the output, correct? Right? Because that 1, remember by shift invariance, is going to have the same one line going downwards everywhere, correct? Which means that every input will be copied to the output. And that will produce a output signal. The output signal is going to be a copy of the input signal. Is that a scale of the input signal? Yes. What is the eigenvalue? Eigenvalue is 1. So any signal is an eigenvector and eigenvalue is 1. Easy enough. What if the weight was, let us say, -3? Any signal is an eigenvector. What is the eigenvalue? -3 is the eigenvalue. Okay? By the property that I told before. Okay. I am going to go with this as an example. This as a convolution, okay? What does this convolution do? Shifts the signal right by 3 samples, 3 addresses, 3 indices, okay? Or if this was the time axis, then I could say that what does it do? It delays the signal by an amount of 3 samples worth of time, correct? Agreed? Does this convolution have an eigenvector? All ones is an eigenvector, he says. Why? Because all ones will come out. All ones. What is the eigenvalue? 1 is the eigenvalue. So, very nice. We found at least one eigenvector. All ones go in, all ones come out. Any other eigenvector? 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Is that an eigenvector? 1, 2, 3, 1, 2, 3. Why? Because if you take that repeating tile 1, 2, 3, delay it by 3, you cannot actually tell whether the delay has happened. It will align exactly with 1, 2, 3. Correct? You understand that? Very easy, right? So 1, 2, 3, 1, if that is what was happening, this 1 will end up here, exactly under this one. Correct? This 3 will end up here. 2, 1. So mechanically what is happening is there is a delay. But it turned out that the output is a scale of the input. Right? You cannot, the shift has kind of disappeared because of it being this specific eigenvector. The shift has happened, but it has disappeared. You cannot see it anymore. You could visualize this as a scale. What is the eigenvalue? 1. Is that correct? So not just 1, 2, 3. What are you actually saying? Any signal with a periodicity of 3, correct? Which repeats itself after 3 samples is going to be an eigenvector with an eigenvalue of 1, correct? Write this. If we consider zeros to the left and right, this won't work. This is important to note. Is absolutely right. Okay, these eigenvectors, even all one's eigenvector is working only with infinitely many ones. Okay? Okay. The only eigenvector with zeros on both the sides is what? Is the all zeros eigenvector. By the way, coming back to this example, if I put in 0, 0, I haven't even showing you the matrix anymore, but if I put in 0, 0, what comes out? What comes out? 0, 0, because that's true for matrices in general, right? And is this an eigenvector? Yes, it is an eigenvector. With what eigenvalue? Any eigenvalue, right? Because you multiply this by anything, you still get 0, 0. So this is not 0 eigenvalue, it's any eigenvalue. So you leave this out. Usually you will not call the 0 vector an eigenvector because it's meaningless. The 0 vector is always going to come out to be the 0 vector. Okay? Is it okay? No? Okay, no? Okay. Give me an eigenvector of this convolution whose eigenvalue is not 1. Give me an eigenvector of this convolution whose eigenvalue is something other than 1. Till now, all the eigenvectors we have seen of this convolution have had eigenvalues of 1. He is saying 1, 0, 0, 2, 0, 0, 4, 0, 0. Didn't he somehow left out 3, 0, 0? Left out 3, 0, 0. Yeah, he's saying, okay. So he means to do it that way. 1, 0, 0, 2, 0, 0, 4, 0, 0, 8, 0, 0, 16, 0, 0, 32, 0, 0, 64, 0, 0. Is there anything to the left? Half, 1/4, 1/8. Okay, because if it terminated somewhere, you will never get an eigenvector. Okay? That is his claim. That is his claim of an eigenvector. One, 0, 0, 2, 0, 0, and then 0, 0, half, 0, 0, 1/4. Here you have 4, 8, and so forth. Let's see that. So, this 1 goes here, 1, correct? Yes? This half comes here, so this is half, 0, 0, 1, 0, 0. This 2 goes here, so 2, 0, 0. What is the corresponding eigenvalue? Is it an eigenvector, and what's the eigenvalue? The eigenvalue is half. Okay? So we have found an eigenvector with eigenvalue half. Does this make sense? Because this output signal is the input signal scaled by half, because 2 has become 1, 1 has become half. While scaling, you have to maintain the indices. Remember that. Okay? This is okay. Now he is saying any geometric series will work. So what? For example, 1, 0, 0, 3, 0, 0?
I mean, just take the zeros.
Huh?
If you take the zeros out, it might still work.
If you take the zeros out, it might still work.
And then you are actually
So, okay, give me some other numbers then. What do you want? 1,
1, 2, 4, that one's fine. But otherwise, take it.
13927.
Direct 13927, huh? You say direct 139, sorry, not 7. 27, 81, 273 or whatever you get. What do you get? 243, okay. 243 and so forth. And what do you have here? 1/3, 1/9 and so forth. Is that an eigenvector? What is the eigenvalue?
1 by
27.
27.
It's 1 by 20.
1 by 27.
1 by 20.
1 by
1 by 27 is the eigenvalue. Okay. Agreed? Now tell me something. Oh, this much you agree with? Give me an eigenvector of this convolution. Sorry, I don't really have those aligned very well. No? Okay. With an eigenvalue of 1 by 9, that eigenvector still works. Correct? What if sorry, what am I doing? What if I give you this? Is this thing still an eigenvector?
If we repeat all the numbers twice, it will be.
Hmm?
If we repeat all the numbers twice, like 1, 1, 3, 3, 9.
If we repeat all the numbers twice, 1, 1, 3, 3, 9, 9, then it will be an eigenvector.
then you just get it 4 times. Then you repeat 4 times.
Okay, I am trying to show a delay of 2 and a delay of 3, okay? On the two lines, I have a delay or a shift of 2 and a delay or a shift of 3. Those are the two lines I have. My question is this an eigenvector? No? Let's carefully try to see what happens, okay? Let's try to see what comes out under the number 1, okay? Now remember, how do you produce a certain output? Of a convolution, how do you produce a certain output of a convolution? You flip around the scattering rule to produce a gathering rule. Yes, you flip around the way you spread the numbers to produce a way of gathering the numbers, correct? And so, you are going to get this, correct? And so, you have here 1/3, 1/9, 1/27, correct? Weights here are 1 and 1. Agreed? What output did you get under 1?
One by 3 plus 1 by 9. 4 by 9.
You got 4 by 27, correct? Is that okay? 4 by 27. Now, here under the number 3, what will I get? Remember, shift invariance, so the same rule is going to go on shifting, correct? Agreed? So, you have these two lines now, and you got 4 by 9, correct? And what do you notice? Yeah. Right? This is 4 by 27th of 1 and this is 4 by 27th of 3. Seems to be working, doesn't it? Let's try one more just to be sure. 9. And what do we get under 9? And what do we get? Now it's these two things, this, and we add these two things together, what do we get? 4 by 3, which is 4 by 27th of 9. Yes? Does it seem likely at least that this thing actually is an eigenvector of this convolution with the two ones? Come on, what must this mean? What must this mean? Big leap.
Eigenvector of sum of convolution, that's it. Eigenvector of sum of convolution, that's it.
Eigenvectors of some convolutions are the same. Yes.
Okay.
If a certain vector is an eigenvector for one convolution and also for another convolution, it is also an eigenvector of this sum.
Good, which is true. If something is an eigenvector of one convolution and also an eigenvector of another convolution, there is an eigenvector of the summation convolution. And that is a summation convolution of those two individual convolutions, even though we haven't really spoken about convolution summations. That's true. Maybe that's what you were saying as well. Okay. So sum wasn't SOME. Sorry for mishearing you. You meant sum as an addition convolution. Okay. 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 Here's a bigger leap. You ready? All geometric progressions are eigenvectors of all convolutions. All geometric progressions are eigenvectors of all convolutions. We'll see it in a moment. We'll see it in a moment. Write down the statement. Yes.
So the eigenvalues are dependent on the spreading rule of the convolution, right?
Yes.
That's how.
Yes. Please note that we did not say that the eigenvalues will remain the same. Even in this case, we got this eigenvector, but not the same eigenvalues. In one case, you got 1 by 27, in one case, you got 1 by 9, in one case, you got 4 by 27, which are different eigenvalues. Okay? But we got the same eigenvector. Now, what I am claiming is that a geometric series will always be an eigenvector. What is a geometric series? It has got some ratio which you go on multiplying, correct? Right? Let's say alpha. So 1, alpha, alpha square, alpha cube, and so forth, correct? That would be a geometric series, correct? And here you will have 1 by alpha. Let me just write it as alpha raised to minus 1 is fine. 1 by alpha. 1 by alpha squared, 1 by alpha cube, dot, dot, dot. That's a geometric series, correct? Right? Now, a convolution let's say that a convolution had 4 lines, okay, where the number 4 is just for the sake of my blackboard animation, okay, and this has some weights on it, agreed? Okay. Now this times this plus this times this plus this times this plus this times this will produce some answer here, correct? Now look at what happens if I move everything one sample to the right. Now I am trying to calculate the output here. The numbers on the lines are the same numbers, correct? That's what shift invariance means, correct? The numbers on my convolution gathering lines are the same numbers, agreed? The multipliers. If you look at the numbers in the signal itself, here I had 1 alpha, alpha square, alpha cube. Now what do I have? Alpha, alpha square, alpha cube, alpha fourth. So what has really happened then? Everything has become alpha times. And so my output is going to be alpha times. Agreed? Agreed? So this output here is going to be alpha times this output. Now if I take another step, again the inputs I am seeing will become alpha times again, which means that the output I will see here will be alpha times again. Do you agree? And so the output is going to be a geometric series with the same factor alpha that was there in the input. Correct? Agreed? And the last thing I have to say is that any two geometric series, if they have the same factor, they are scales of each other. Any two geometric series having the same factor are scales of each other. Do you see this? Why? It's easy to see, right? Because see, under this fellow 1 there is going to be some number. You don't know what that number is, there will be some number, correct? Now as this goes to alpha, this will go to alpha times that number. So the ratio between this and the ratio between this and this will be the same. Again, one more, alpha times, ratio between the two is the same. Alpha times, ratio between the two is the same. Ratio between an input number and a corresponding output number will always be the same, which means that the output signal is a scale of the input signal. Hence proved. Write it down.
So we can express any, so if we have a different series with same factor, different GP with same factor, then we can express it as a, something times the original signal. So if we have a signal with factor alpha and we have another signal with factor alpha, then we can express second signal as something times first signal.
Correct.
And that will come out of convolution, because that's where.
No, that's true in general. If you have two series having the same vector alpha, they are scales of each other. This doesn't require any convolution, it's just automatically the case. That was just the last step of the proof, because we are trying to prove that a geometric series with some factor alpha, in fact any factor alpha, is going to be an eigenvector. But we ended up proving that a geometric series with a factor of alpha will produce a geometric series with a factor of alpha. And so the last step was to say that, oh, but that's a scale, right? Because it will always be a scale, correct? Do you agree? The proof is okay. Should we go over it again? This is like the most important thing we'll do in this course. So it literally is, it actually is. Everything is downhill from here. In the sense, it's easy if you have reached the top. In that sense, okay? If you have pushed your boulder all the way to this hill, then it's going to roll itself down the rest of the course. If you haven't, you'll have to find your own way around the hill. Huh?
Will it be like Sisyphus?
Yeah, if you have Sisyphus yourself all the way to this, then you can relax after that. Okay, once again, we are trying to prove, this is very important, okay? We are trying to prove that any geometric series is an eigenvector of any convolution, okay? And what is the trick here? The trick is that you write down a geometric series, it has got some factor alpha, right? And then you think of the convolution as a gathering rule, okay? Now, the amazing thing about the geometric series is, if you look at it in some window and then you shift the window, it is as if the geometric series has scaled, okay? And so, what does a convolution do? It looks at numbers in a window and multiplies them by some numbers and produces an output, correct? Now, if you are trying to produce the next output, this window will shift, which means the input numbers will scale by that factor alpha, which means your output will scale by that factor alpha, right? Which means that just like the input is scaling by alpha, 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 the output is also scaling by alpha, 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 which finally means that the output is a scale of the input. Why? Because whatever is the scale between the input and output for some particular sample, that scale will always be maintained. That ratio between the input and output samples will always be maintained because both of them are getting multiplied by alpha every time. Okay? That is the entire proof. That is the entire proof of the theorem that any geometric series is an eigenvector of any convolution. Now that this gives you a large set of eigenvectors to analyze convolution. You remember initially for that 2 by 2 matrix we found 2 eigenvectors, and that allowed us to understand the behavior of that 2 by 2 matrix in a different geometric way. In some similar spirit, we now have a large set of eigenvectors for any convolution. And now we are going to do a trick. How about using a complex geometric series? We studied complex geometric series in the last lecture. How about using a complex geometric series? This requires some explanation, okay? We already have the possibility of defining complex valued signals. You remember that? Where every sample of the signal is a complex number, okay? Or two-dimensional vector, correct? You remember that? Skipping rope signal, right? Right? So your samples are on planes like this, and every sample is pointing in some direction and has some length, and that's a complex number, okay? Is this fine? So it's a complex valued signal. Let's say I allow this for a moment. Can you also imagine a complex ruled convolution? Basically, directly think of the gathering. Just these weights are complex numbers. And the multiplication is going to be complex multiplication. Okay? What does this mean? Maybe it means nothing. It's an arbitrary game we are playing for the moment. Okay? Okay? Will that produce a complex number at the output? It will. Can I go on looking at various values of the signals and producing some output, some output, some output? I can. This much is fine. So complex valued signals going into complex ruled convolutions coming out to give other complex valued signals. Is that okay? That is okay. Okay. What if I have this as my mathematical structure, complex valued signals and complex ruled convolutions, but all the numbers happened to be the real numbers inside complex numbers. You remember there are kind of real numbers inside complex numbers, numbers that behave exactly like real numbers sitting inside the complex numbers. Remember that? Yeah, we spoke about this, correct? Yes. So, if the numbers going in are allowed to be complex numbers but all happen to be real numbers, if my weights are allowed to be complex numbers but all happen to be real numbers, what will come out?
The outputs are complex numbers but happen to be real numbers.
Complex numbers that happen to be real numbers. Agreed? Furthermore, this entire thing will exactly mimic the corresponding real signal going into the corresponding real convolution. Is it okay?
It's the same as Fourier. We can use the signal as a complex signal.
We haven't, now we will.
But it will look the same mathematically.
Mathematically, it will look the same, yes. Is this okay? Is it okay? So, with that much of a background, now I say, throw out the real signals and real convolution and let's think about complex signals and complex convolution. Okay? Now, here we allow complex numbers. These weights also we allow complex numbers. Right? These outcomes will also be complex numbers. Geometric series can now be more kinds of geometric series than real number geometric series is allowed us to do. Right? For example, can you imagine some geometric series which is a complex geometric series which is not a real geometric series or even a real like geometric series? Just give me something. alpha equals I. Okay, alpha equals I. What do we get? 1 I square is minus 1. Remember 1 I square is minus 1 minus I 1 I minus 1 minus I 1 I minus 1 minus I 1 I minus 1. If everything we are saying is supposed to work and it ought to work, then that thing has to be an eigenvector of any convolution, right? Right? But that's a periodic signal. So now we start getting periodic eigenvectors of convolutions. In fact, of any convolutions. Let's go into a 5-minute break and we will see what it is that we have actually derived. 5-minute break. You remember Archimedes? Archimedes did a lot of things. One of the things he invented was the screw, the water screw. To be more specific, is basically a screw that goes down into a well, and if you turn the handle, then water comes up, right? Those kinds of pumping mechanisms still exist, by the way, and people use them in the oil and gas industry, for example, to pump out oil. They are known by other fancy names now, not just water screws, but they are still used, right? Why is the water coming out? Kind of. What makes the screw such a amazing mechanism or machine? The water can't tell if the screw is rotating or the screw is shifting. Does this make sense? That's the mechanism of the screw. You can't tell. I mean, just visualize a screw. You have all seen a screw going into the wood, right? Just like a normal, right? Just visualize a screw, right? It has got this thread going around it, right? In a spiral. Let's call it a spiral. Okay, better word would be helix, but that's hard to remember. Spiral is an easy word, right? A thread. You know what a screw is, what a thread. Come on, I know you are not engineers, but you know this much, right? So, yeah, correct. So now imagine it rotating. If you rotate, you saw that movie, it will seem as if things are just shifting, correct? You have seen this kind of movie somewhere or something, right? Yeah? And that's the beauty of the screw. You cannot tell whether it's rotating or it's shifting. That is why if you rotate it, it actually moves. Right? That is the way our fans work, for example. What are fans? They are just screws in the air. That's what they are, literally. That is what they are. What are propellers on an airplane? Right? Correct? And they have these blades which are literally screws. The propeller is not, it's even called an air screw. Look it up. I am not making this up. The old term for a propeller is air screw. If you look up aviation textbooks from the 1940s, they are not called propellers, they are called air screws. Okay? So, and it's rotating, but the air thinks it's moving through it. So, the air moves this way, which as a reaction force causes the plane to move that way. let's take something, right? Okay, so let's take this signal. I'm going to take a signal. Let's take 1, and then the next thing is going to be 1 at an angle of omega. Okay? 1, which means 1 at an angle of 0. Okay? 1 is the same as 1 at an angle of 0. Next thing is going to be 1 at an angle of omega. These are complex numbers. What will be the thing after that? 1 at an angle of 2 omega. Okay? 1 at an angle of 2 omega. Do you realize I am building a geometric series? Yes? With a factor of 1 at an angle of omega. Because if I multiply this with 1 at an angle of omega, I actually get 1 at an angle of 2 omega. That is the brilliance of complex multiplication, that the angles are added. You will see why this is so brilliant. This is 1 at an angle of 3 omega and 1 at an angle of 4 omega. What do you have here? 1 at an angle of minus omega, correct. 1 at an angle of minus omega, 1 at an angle of minus 2 omega, 1 at an angle of minus 3 omega. Okay? Now to produce some output, you have a convolution. To produce some output, you are going to multiply these numbers by some numbers. Okay? For the simplicity of visualization, I am going to take these numbers to be realish numbers. Okay? Real numbers within complex numbers. Okay? Just for the simplicity of our visualization. Okay? So what is happening is these complex numbers get multiplied by these realish numbers, which scales those vectors. Then all those vectors add together. Remember, complex numbers are two-dimensional vectors. All those vectors add together to produce an output vector. Agreed? Okay? If I were to visualize this on the complex plane, so I have this, right? Okay, so I have 1 here, I have 1. This is 1 at an angle of omega. This is 1 at an angle of 2 omega. This is 1 at an angle of minus omega, correct? These are the 4 numbers. Agreed? These are these numbers in that window of numbers.
Omega is some arbitrary.
Omega is some angle. I am not specifying it right now. Omega is some angle. But whatever it is, it's fixed. Is it okay? And these numbers will scale each of these numbers by something. These numbers will scale each of these numbers by something. I am just taking them to be real-like numbers so that the scales point in the same direction just for the ease of visualization. It doesn't have to be that. I am just doing it for ease of visualization. Okay? And then all these 4 complex numbers add up to produce some complex number, which would be, let us say, here. Okay? It produces this complex number. Is that okay? Now, when I go to calculate the next output here, what happens? Now my 4 complex numbers are 1, 1 at an angle of omega, 1 at an angle of 2 omega, and 1 at an angle of 3 omega. And they will get multiplied by the same numbers. By the same numbers, and that will produce an output. Correct? What can you say about the relationship of this output and this output? This output is this output rotated by omega. Do you understand this? Why? Because all these input numbers got rotated by omega, isn't it? Since all the input numbers got rotated by omega, the same scaling happened, addition happened, the output has to rotate by omega. What will happen as I go one step further, one index further? Again, all the inputs will rotate by omega, again the output will rotate by omega. Again, all the inputs will rotate by omega, again the output will rotate by omega. Okay? And so, the output here, we don't know, it's some complex number, but it is going to go on rotating by omega, 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 omega. Does this make sense? Yes? This is basically the Archimedean screw. Right? You cannot tell the difference between a shift and a rotation. As you shift the window in time, the values look as if you have rotated the values. Correct? Right? What does this, if I were to plot it out, what will it look like? You remember how we plot complex signals? How do we plot complex signals? In that in that line format, right? So if I were to plot this, I will plot it on planes that look like this, correct? Correct? What will this signal look like plotted out in this fashion?
What does the square represent?
The square is individual complex planes, right? The square is individual complex planes. Remember this. So this is 1 here, this is 1 at an angle omega, this is 1 at an angle 2 omega, this is 1 at an angle minus omega, this is 1 at an angle minus 2 omega. Yes? What is the shape this is forming? It is forming a screw, do you see that? It's forming a spiral around that central axis. Do you see this? Yes, it's forming this spiral around that central axis. That's what this is doing. Okay. And as I shift my convolution window, actually I am shifting. But shifting for a screw is like rotating the screw. And so as I shift my convolution window, it is as if the values have rotated, which then rotates my output by an equal amount. Okay? And so the output is always going to be rotated by omega. So whatever is the output here, the output here will be this output rotated by omega or multiplied by 1 angle omega. Correct? We are saying the same thing we said before. Algebraically, we are saying nothing new. Geometrically, it looks very new. Algebraically, all we are saying is that this is a geometric series which is an eigenvector of a convolution. Algebraically, nothing new has happened. Geometrically, it looks very different because now geometric series look very different. They look like these spirals. Is this okay? Is it okay? Now, if you have this, if this eigenvalue sorry, if this convolution is some convolution f, my question is, okay, my first question is, have we proved ourselves that for any fixed omega, this is an eigenvector of that convolution, any convolution? Are we in agreement there? For the same reasons, we got an output screw that is also rotating by omega, which is going to be a scale of this. Now that scale here means complex scale, okay? What does complex scale mean? Do you remember what does a complex scale mean? You are allowed to, what do you do in complex scaling a complex signal? You are allowed to scale the signal and rotate the signal. Agreed? Remember this? Just 2 lectures ago, which unfortunately was a month and a half ago. Okay? So, do you agree that this is a complex scale of this? Yes? This is a screw with a stepping angle of omega. This is another screw with a stepping angle of omega. It might have a larger thread or a larger radius. It might start from a different angle, but they both have the same stepping angle of omega. So you can scale one of them and rotate it to exactly fit the other. Does this make sense? So this is a complex scale of this. Yes? And so this is an eigenvector of this, or this is an eigenvector of this. Correct? And now my question is, what is the eigenvalue? To calculate the eigenvalue, it is enough for me to actually calculate this value. Do you agree? This value, this complex number is in fact the eigenvalue. Correct? Why? Because 1 becomes this. So if 1 becomes this, then 1 angle omega times this will be this, correct? So this value itself, the value that goes under 1 is going to be the eigenvalue. The value that goes in the same index that 1 went into is going to be the eigenvalue, because 1 scaled to this. So the scale factor has to be this number itself. Agreed? So to calculate the eigenvalue, all I have to do is actually just calculate this number. Agreed? But calculating that number is just calculating the convolution, isn't it? Correct? At that particular this thing. And so let's calculate the convolution. What do we get? Basically we have to take, you have to take all of these lines, correct? There could also be lines, we don't know how many ever there are. What is the label for this line? What is the weight or multiplier for this line?
Some W, I guess.
No, in terms of f. In terms of f, what is the multiplier on this line? F0, correct. So this is F0. This is F0. What is the weight on this line? F1, correct. Going left, we are gathering, so it has flipped around. So F1. F1. What is the weight on this line? F2. What is the weight on this line? F minus 1. Correct? Do you agree? Okay. How many ever there are. How many ever there are. And so, what is the value here? Calculate it. Calculate it. Summation something, something, something. Do it.
Summation of f of I multiplied by 1 rotated by minus I.
Summation something. No. Summation what going from what to what? 1 going from? I know 1 and I are two things which I have been saying are very similar. So I started using 1 instead of I. Let's not use I. The J. Some engineers will have a hard time with J. Let's leave out I and J. They are both for the imaginary number now. K is good. K going from minus infinity to infinity. F of K into minus K omega. Agreed? Right? Agreed? Which, just to make it look textbook like, we will use textbook notation instead of our famous angle and turn notation, which, by the way, let's say omega is radians, so I don't have to convert between turns and radians for the time being. Summation K going from minus infinity to infinity, f of K. Anyone? E raised to minus I K omega. Okay? What is this? This is the eigenvalue corresponding to the eigenvector which is rotating at a speed of omega angles per sample. Eigenvalue corresponding to the eigenvector, that is a screw rotating at omega per sample. Agreed? Give me a moment, give me a moment. This thing is called the discrete term Fourier transform of f. Shortened in many textbooks as DTFT. Many textbooks directly use time notation, so that they might say discrete time Fourier transform, still shortened as DTFT. Once again, what is the Fourier transform? The Fourier transform of a convolution rule at a particular rotation speed omega is the eigenvalue that a spiral of that rotation speed suffers when passed through that convolution.
You repeat the definition.
It's not the definition, this is the definition. I will repeat the description. The discrete term Fourier transform of a convolution rule f is of a convolution rule f for a particular rotation speed omega is the eigenvalue that the spiral of that rotation speed suffers when passed through that convolution. If you understand this single sentence, that whole 500-page book becomes a single sentence. Okay, you can open any page and read directly if you understand this single sentence. Convolution rule
Is arbitrary, right? It can be anything.
is arbitrary. It doesn't have any omega built into it. The convolution f is allowed to have any complex numbers, and specifically you are usually interested in real number convolutions. So this will usually have real within complex numbers f. Okay.
What do you mean when we say Fourier transform convolution rule f at particular rotation speed omega?
No, I didn't say that. The spiral has a rotation speed omega. The eigenvector we are talking about is a spiral with a rotation speed of omega per sample. Correct? Look at this. 1, then 1 angle omega, 1 angle 2 omega, 1 angle 3 omega, 4 angle 5. It's right? Huh. Suffers the spiral of the rotation speed omega per sample. That's what I said, I think, both the times. Has anyone else written down exactly what I said? Okay. Spiral. Insert the word spiral if you don't have it. Okay. Is this okay?
Can you repeat once finally?
Did anyone write it down exactly? Please repeat it. So hard to repeat something. So I have to say that. Okay. Let me say it again. Come on. I can say it the third time. Let's say it one more time. The Fourier transform of a convolution rule at an angle omega. That's where I said at an angle omega. Correct. Because the Fourier transform requires the angle or angular speed omega. Okay. At the angular speed omega.
What do you mean by rule at angle omega?
This rule can be, what do you need to calculate this value? You need the convolution rule f.
Which is spreading a signal which is rotating at an angle omega.
No, convolution rule f is allowed to do anything. Convolution rule f is just convolution rule f. Yeah. Right? We will analyze it as having a particular eigenvector and find its eigenvalue for that eigenvector. In general, it's allowed to do anything. So, to calculate that, we need a convolution rule f, and we need an answer to the question of what eigenvector are you calculating the eigenvalue of. And what eigenvector? It is the eigenvector that is the spiral rotating at a rotation speed of omega angles per sample. Is this okay? Let's see a quick outcome. Okay? Quick outcome. Suppose I have a convolution, some convolution, okay? And in goes a sine wave. Just a real physical situation, real numbers, okay? In goes a sine wave, some convolution. Maybe this hall is producing echoes, whatever, something. Question is what comes out. Now, just for the sake of analysis, we will upconvert all of this to complex numbers. Same sine wave, but now complex numbers, the imaginary part is always 0. Okay? Okay? Is okay? Same numbers here, but now also with imaginary part 0. It will produce the same numbers at the output, correct? Right? Their imaginary parts will have to be 0 because nothing actually has any imaginary parts. Right? Exact same thing is happening. I am just using complex numbers for the sake of argument at the moment. Now, this sinusoidal, I can break it up into what?
Periodic.
Points.
Look at this. Imagine two vectors going around like this. What is the resultant? It will not be 0. What is the resultant at this moment, for example? Parallelogram law here. Here, right? Now I go here, what happens? It starts coming, right? It's like the old, have you seen old elevator doors? It kind of looks like that, okay? And it goes all the way to 0, then it goes down there, then it again goes to 0, then it goes up here, then it goes to 0. What is it creating? What is it creating? What is it creating? A sine wave. A sine wave. Huh? You had this sometime in school, college, somewhere, 2 UCMs give 1 SHM, remember? Uniform circular motions and simple harmonic motions are related in some fashion. Remember this? That's what I'm talking about. Correct? Right? Now, since this sine wave is actually happening in complex numbers, I can break it up into these two things. But what are they? They are these spiral screws in time. Aren't they? Aren't they? Agreed? Yes? The summation of these two rotations is actually this simple harmonic motion. Sorry, my real axis is now vertical, but it makes it easy to show what's happening. Okay? My real axis is vertical. Okay, imaginary axis became horizontal. Mathematics is arbitrary. It's okay. Agreed? Yes? In your mind, split this up into the two screws whose summation becomes this thing and pass each of them individually through the convolution. What happens? They come out as spirals of the same rotation frequency, isn't it? That's what we proved. They come out as spirals of the same rotation frequency. Now, if they get added at the input, correspondingly, the outputs must add by linearity of convolution, correct? Correct? And so, these two spirals at the output, still rotating opposite to each other, must add to again produce real like numbers. Which means what will they produce?
Periodic.
Even more specifically, a sinusoidal of the same frequency. And so we just proved in a matter of a few seconds that a sinusoidal passed through any convolution will produce a sinusoidal of the same frequency at the output. This is, by the way, the reason that you can all hear me speaking even though a terrible convolution is happening between us. Why? because both my sound production mechanism and your sound reception mechanism is tuned to producing and detecting sinusoidals. Nature programmed us this way. Why? Because nature knew that one day we would sit in lecture halls and try to understand things. I don't know if evolution was that super intelligent, or God, or whoever designed us. But, you know, I'm sure cavemen were having lectures.
No, it would be to protect them from danger things.
Right. Cheetahs in the dark part of the cave, I don't know. Okay. Convolutions and undoing convolution was important evolutionarily for various reasons. Correct? And thus, we got programmed by nature, God, call it what you will, to have sinusoidal production and sinusoidal reception so that the problem of this arbitrary difficult convolution disappears. Isn't that amazing? And in turn, when we created our own communication systems, like all of these 3G, 4G, 5G, 6G, 8G, all based on sinusoidals. We even give them like 1.2 gigahertz. We even like to give them names and say this costs this much, that costs that much. We actually put a price on spirals. Why are they so important? Because they are the ones that work around the problem of multiple buildings convolving through multiple pathways, the signal that I am producing reaching your mobile phone, which would otherwise be entirely destroyed. Okay? The reason sinusoidals occur so frequently in nature, or sinusoidals seem to occur so frequently in nature. Maybe they don't occur in nature, but they occur in our analysis of nature. Right? Maybe waves on water are not sinusoidal, but in our analysis they are sinusoidal. Why? Because water is the waves on water are a partial differential equation, almost linear, almost shift invariant. Anything that's linear and shift invariant is a convolution. So waves on water are a convolution. You analyze them using sine waves and you start seeing waves on water. Okay? Everything. Why does a guitar string move sinusoidally? Same reason. Okay? So, one very simple answer is sinusoidals always produce sinusoidals. Came out of this extreme amount of effort that we took convincing ourselves that spirals always give spirals. One last point for the day. It is, by the way, traditional to call this. So, if the convolution rule is called F in many textbooks, its Fourier transform will be called capital F. Okay, so capital F at the frequency omega. Capital F is the Fourier transform of small f, is how many textbooks will write it. Suppose I have two convolutions, star f, star g, correct? This is equivalent to one convolution. Do we know that? We know this very well. One convolution with some convolution rule, say h, which equals, h is going to equal f itself convolved with g, correct? Right? And you remember the proof of that, right? I mean, you want to find the combined impulse response, but that is just impulse response of the first step will just be f, that will convolve through g, and so what will come out if an impulse went in would be f star g, and hence the impulse response is going to be f star g, and a convolution gives a convolution whose impulse response is f star g. We have seen this before. Agreed? Agreed? Now, if you think about this from the point of view of an eigenvalue, a spiral went in, what will come out? Another spiral will come out, but this spiral will be scaled and rotated. The scale and rotation will be what? If this spiral has a angular speed of omega, this spiral will get scaled and rotated by what amount? By the complex number f of omega, correct? Correct? Now remember, it's still a spiral rotating at omega, which means it is still an eigenvector, isn't it? Because you scale an eigenvector, it's still an eigenvector. So what will happen to this still an eigenvector as it passes through G? This thing will get scaled further by the Fourier transform of G at omega. Correct? Is this correct? Yes. And so then if I put the same spiral here, what is the corresponding eigenvalue? It's not hard. What comes out here has to be exactly what comes out here, right? And what comes out here? It is this thing scaled by f of omega, then scaled by g of omega, which means it is this thing scaled by f omega into g omega, and so h omega has to be f omega g omega. Right? Which demonstrates that this is very important. Convolution in the signal domain is just multiplication in the Fourier domain. That's the whole point of eigenvectors actually. That something that is very complicated becomes just a multiplication, just a scale. So we actually designed the entire thing for this to come out. This ought not to be surprising, actually. This is the fundamental theorem of Fourier transforms, that convolution in the signal domain is just multiplication when you look at it in the Fourier domain. What we haven't proved yet, and what we will now prove in the next lecture, is the following, that the Fourier transform way of analyzing convolution is a complete way of analyzing the convolution. Okay? Just like that first simple 2 by 2 matrix that I gave you, if you knew the eigenvalues to those two vectors, you could calculate what any input will do, correct? Why? Because those two vectors were such vectors such that any other vector could be written as a sum of those two vectors. This is something I have not shown yet, but we endeavor to show next time, that these eigenvectors that we have found, you can represent not just sinusoidal inputs, but any inputs, any inputs as a summation of these spirals. And if you show that, then the Fourier transform way of looking at things is a complete picture of what any convolution does. A convolution does nothing outside what its Fourier transform does. Okay? And that is what will make these Fourier transforms such a powerful tool for analyzing any convolution. We have already, I have been saying all the while why convolution is important. We have gone half the way to showing you how convolutions do something brilliant with certain shapes. Now I will show you that next time that that's an entire analysis of convolutions. And that is essentially the Fourier transform theory, which is signal processing theory or image processing theory or anything. Lots of physics, everything in physics, everything you do is actually just this. You call it block waves, you could give it 100 different names in 100 different domains. But most of the times it's convolutions and you're analyzing it using something like this. Thank you very much. I will see you on next Thursday at 5. Have a good weekend. Bye-bye.